The Fermi Paradox is the greatest mystery in science. But what if the reason we can't find the answer is because the question itself is wrong? Welcome to the Purple Files. If you enjoy our videos, please consider subscribing to the channel. Let's get right into it. The Fermi Paradox is built on a simple and perhaps dangerously arrogant assumption that Earth is typical. That our planet, our star, and our neighborhood are unremarkable. Just one of billions of similar systems in the Milky Way alone. If that's true, then life should be everywhere. But this first theory challenges that foundational premise. It suggests the paradox isn't a paradox at all, because its starting assumption is fundamentally wrong. This is the rare Earth hypothesis, and it argues that the chain of events that led to intelligent life here was so extraordinarily long, so improbable, and so dependent on a series of cosmic flukes, that Earth may not be one of billions, but one of one. We are not looking at a paradox, we are looking at the winning ticket from a galactic lottery of impossible odds. Let's break down just how many things had to go perfectly right. First, our location. We live in what's called the galactic habitable zone, too close to the galactic center, and the sheer density of stars, the supernovae, and the intense radiation from the central supermassive black hole would sterilize any nascent life. Too far out in the galactic suburbs, and there aren't enough heavy elements, the metals forged in the hearts of stars, to form rocky planets like ours in the first place. We are in a quiet, stable Goldilocks orbit around the entire galaxy. Next, our star. Our Sun is a G-type main-sequence star, known for its stability and longevity. It burns steadily for billions of years, providing the stable energy needed for the slow process of evolution. The most common stars in the galaxy are red dwarfs, which are tempestuous and violent. They blast their nearby planets with lethal flares of radiation, and any planet close enough to stay warm would be tidally locked, with one side perpetually scorched and the other perpetually frozen. Our Sun is a gentle giant in a galaxy of angry pygmies. Then there is our solar system's architecture. We have Jupiter, a colossal gas giant that acts as our cosmic bodyguard. Its immense gravity sweeps through the solar system like a bouncer, deflecting or absorbing countless comets and asteroids that would otherwise be on a collision course with Earth. Without Jupiter, our planet would be subjected to a catastrophic impact event, not every 100 million years, but perhaps every 100,000 years, constantly resetting the evolutionary clock back to zero. And what about the Earth itself? It had to be the right size, large enough to retain a molten core which generates the magnetic field that shields us from deadly solar wind, but not so large that it held onto a crushing hydrogen atmosphere and became a gas giant. But perhaps the most crucial and rarest feature is our moon. Our moon is freakishly large in comparison to its planet. It was likely formed from a cataclysmic collision with a Mars-sized object early in Earth's history. This massive moon acts as an anchor, stabilizing our planet's axial tilt. Without it, Earth's axis would wobble chaotically over geological time, leading to wild, unpredictable swings in climate that would make the evolution of complex life impossible. Finally, there is the miracle of plate tectonics. This constant recycling of the Earth's crust is vital. It drives the carbon silicates cycle, which acts as a global thermostat, regulating our planet's temperature over eons. It creates the continents and oceans, fostering biodiversity. Many rocky planets may be dead worlds with a single solid crust. They might have the ingredients for life, but no engine to stir the pot. When you multiply the low probability of all these factors, the right galaxy, the right star, the right planetary system, the right planet, the right moon, and the right geology, the number of candidate worlds for intelligent life plummets. The rare Earth hypothesis argues that while simple microbial life might be common, the jump to complex, intelligent animals like us is so fantastically rare that the silence we hear from the cosmos is not a mystery. It is the expected, logical state of a universe where we are, for all practical purposes, utterly and completely alone. The Fermi Paradox carries a heavy assumption about time, It presumes that since the universe is nearly 14 billion years old, other civilizations must have had billions of years to evolve and expand before we ever showed up. It paints us as latecomers to a party that has been going on for eons. But what if that assumption is wrong? What if the universe itself is only just now becoming a truly hospitable place for complex life? This is the firstborn or early bird hypothesis. It suggests that we are not late to the party at all. We are among the very first guests to arrive. The reason we see no signs of ancient galactic empires is because none have ever existed. To understand this, we have to look at what the early universe was actually like. It was not a quiet, peaceful place. The first few billion years after the Big Bang were an age of cosmic violence. Galaxies were crashing into each other, star formation was happening at a furious rate, and the cosmos was riddled with sterilizing radiation. Quasars, the hyperluminous cores of young galaxies, powered by feeding supermassive black holes, blasted out jets of energy that could strip the atmosphere from any nearby planet. And even more terrifying were gamma-ray bursts, or GRRBS. These are the most powerful explosions in the universe, thought to be caused by the collapse of massive stars. A single nearby gamma-ray burst would be a planetary extinction event, its radiation boiling away oceans and destroying DNA on a hemispheric scale. In the early, more compact universe, these events were far more common. The universe was simply too hot, too chaotic, and too radioactive for the delicate multi-billion-year process of evolution to proceed uninterrupted. Beyond the raw violence, there was a problem of ingredients. The Big Bang created only the lightest elements: hydrogen, helium, and a tiny bit of lithium. Every other element on the periodic table, the carbon in our bodies, the oxygen we breathe, the silicon in the rocks beneath our feet, had to be forged in the nuclear furnaces of stars and then scattered across the cosmos when those stars exploded as supernovae. This process of enrichment is incredibly slow. It takes generations of stars living and dying to build up enough heavy elements, what astronomers call metallicity, to form rocky terrestrial planets and provide the raw materials for life. The early universe was elementally poor. It was a cosmos of gas, not of worlds. So when you combine these two factors, the constant sterilizing violence and the slow build-up of essential elements, a new timeline emerges. The universe may have had a long multi-billion-year preparation phase where complex life was simply impossible. The window of opportunity, the cosmic habitable era, where a galaxy is calm enough and element-rich enough for a species like us to evolve, may have only opened relatively recently in cosmic terms. If that is the case, then humanity is not an anomaly for its tardiness, but a pioneer. We could be part of the very first wave of intelligent life to emerge in the Milky Way. If we are the firstborn, then the silence of the cosmos makes perfect sense. There are no ancient alien signals to hear. There are no Dyson spheres dimming distant stars. The sky is empty because we are the first ones to turn on the lights. The great silence is not the sound of a graveyard. It is the sound of an empty nursery, waiting for others to wake up. The Fermi Paradox creates a powerful expectation. If aliens exist, they should be obvious. Their signals should be flooding our airwaves. Their star-spanning empires should be visible to our telescopes. This theory argues that this expectation is born from a profound failure to grasp the sheer, mind-numbing scale of the universe. The reason we find no evidence of aliens is not because they aren't there, but because we are looking for a needle in a haystack the size of a galaxy. The problem is not a lack of aliens, but a problem of scale. Let's start with the scale of space. Our galaxy, the Milky Way, contains an estimated 200 to 400 billion stars. Our search for extraterrestrial intelligence, the SSEI program, has in its entire history scanned only a few thousand of those stars in any detail. The famous analogy is that our search so far is equivalent to scooping a single glass of water out of all of Earth's oceans and concluding, based on that sample, that there are no whales. But even that analogy fails to capture the true scale. It's more like looking for a single, specific, marked grain of sand on all the beaches of the entire world, and our search has so far only examined a small bucketful from one beach. The volume of space we have meaningfully searched is statistically zero. 1,000 civilizations could be broadcasting right now, but if they're not in the tiny sliver of sky we happen to be looking at, with the right frequency at the exact right moment, we would never know. Now let's add the even more daunting scale of time. Our planet has existed for 4.5 billion years. Intelligent human civilization has existed for a few thousand years, and our ability to send or receive interstellar radio signals is only about 100 years old. Let's imagine a hypothetical advanced civilization. Perhaps they thrive for 1 million years, a massive span of time to us. But what if they are only radio loud for a small fraction of that time? Perhaps they use radio for 500 years before discovering a new, more efficient technology and going radio silent. The chance of our tiny 100-year listening window overlapping with their tiny 500-year broadcasting window across a gulf of billions of years is almost zero. The galaxy's history is a 4.5 billion year-long film, and we are trying to find another civilization by peeking at a single random frame. Finally, there is the scale of energy and direction. The inverse square law dictates that a signal's strength decreases drastically with distance. A broadcast like our own television or radio signals becomes indistinguishable from background noise just a few light years away. For a civilization on the other side of the galaxy to be heard by us, they would need to be broadcasting a signal of almost unimaginable power, and they would have to aim it directly at our solar system. Why would they? Most communication would be local. This all leads to a powerful conclusion. The galaxy could be teeming with life. It could be a vibrant, noisy place filled with thousands of civilizations, each living in its own stellar neighborhood, communicating locally, living and dying on timescales we can't comprehend. But because of the crushing, absolute vastness of space and time, they are all effectively isolated islands in a cosmic ocean. The Great Silence is not a sign of absence. It is a symptom of distance. It is the natural sound of a universe that is simply too big for a young species like us to hear anyone else's voice. The Fermi Paradox assumes that if aliens were trying to communicate, we would be able to recognize their message. It assumes that they would use a method of communication that is intelligible, or at least detectable, to us. This theory challenges that assumption by suggesting that we are so technologically primitive that we simply don't have the right tools to join the conversation. The reason we hear nothing but silence is because we are fundamentally deaf and blind to the real galactic dialogue. We are listening for drums in the age of Wi-Fi. Our entire search for extraterrestrial intelligence is built around radio waves. Why? Because radio is what we discovered. It is a technology that is barely a century old, and we project it onto the entire universe, assuming that any other intelligent species would use it too. From an advanced perspective, radio is a terrible way to communicate across interstellar distances. It is incredibly slow, taking thousands of years to cross the galaxy. It is inefficient, requiring enormous amounts of power to send a coherent message over a long distance. And it is not private. It broadcasts in all directions, making it easy to intercept. It is, in every sense, a primitive technology. To assume that a civilization 1 million years more advanced than us would still be using radio is like assuming the Roman Empire would have communicated with smoke signals instead of building roads. So what would they be using instead? We can only speculate, but the possibilities are mind-bending. They could be using modulated neutrino beams. Neutrinos are subatomic particles that barely interact with matter, meaning they could be beamed directly through entire stars and planets without being distorted, making them perfect for a point-to-point galactic internet. We can barely detect neutrinos, let alone send messages with them. Or perhaps they communicate using gravitational waves, ripples in the fabric of space-time itself. We only gained the ability to detect these in 2015. The idea of encoding information in them is pure science fiction for us. And what about technologies that are even further beyond our comprehension? Perhaps they use quantum entanglement for secure instantaneous communication across a pre-established network of probes. Or maybe they have mastered higher dimensions, sending information through a reality that we cannot even perceive. The most likely answer is that an ancient civilization would communicate using principles of physics that we have not even discovered yet. Their signals might be passing through us, through our planet, right now, a flood of information as obvious to them as Wi-Fi is to us. But we lack the sensors, the organs, the technology to perceive it. We are like an uncontacted tribe on a remote island, listening for the sound of drums, completely unaware of the thousands of satellite communications passing invisibly over their heads every second of every day. This theory reframes the Fermi Paradox not as a mystery about the absence of aliens, but as a humbling lesson in our own technological infancy. The great silence may not be a silence at all. It might be a cacophony of voices, a symphony of signals so advanced and so complex that it is completely imperceptible to us. The paradox doesn't exist because the universe is empty, but because we are not yet advanced enough to be part of the conversation. Our final theory is perhaps the most mind-bending of all. It challenges the most fundamental assumption of the Fermi Paradox, the assumption about alien motivation. We assume that advanced life would be expansive, energetic, and visible, just like us, only more so. This theory, known as the Aestivation Hypothesis, proposes the exact opposite. It suggests that the most advanced civilizations in the universe are deliberately doing nothing. They are hiding, not from us, but from the laws of physics itself. The great silence is the sound of the galaxy taking a nap. Aestivation is a biological term for a state of dormancy, like hibernation, but used to survive periods of heat and drought rather than cold. In this cosmological context, it suggests that mature civilizations have gone dormant to wait for a colder, more efficient future. The logic proposed by futurists at Oxford University is chillingly sound. It begins by asking, what is the ultimate goal of a super-advanced, likely post-biological digital civilization? The answer is not conquest or expansion, but computation. Information processing is the ultimate currency. The ability to think, to simulate universes, to experience consciousness, that is the final frontier. Now we must consider the laws of thermodynamics. A fundamental principle of physics known as Landauer's principle states that every time a computer performs an irreversible operation, like erasing a bit of information, it generates a tiny, unavoidable amount of heat. This means that computation itself has a physical cost. To perform more calculations, you need more energy, and you need to manage the waste heat. Here is the crucial insight. The energy cost of computation is directly tied to temperature. According to the laws of physics, the colder your computer is, the more computation you can perform for the same amount of energy. The efficiency of information processing increases dramatically as the temperature drops towards absolute zero. So imagine you are a civilization that has been around for 1 billion years. You have mapped the laws of physics and you understand this principle perfectly. You look at the universe around you. It is still young, hot, and full of wasteful background energy from the cosmic microwave background. You realize that burning through your precious energy resources to perform computations now, in this relatively hot era, is incredibly inefficient. It's like running a supercomputer in an oven. The logical, optimal strategy is to wait. You would gather resources, convert your civilization into a state of pure information, build the most massive computational structures possible, and then go to sleep. You enter a state of dormancy, estivating for trillions of years until the universe has expanded and cooled to a fraction of its current temperature. When you reawaken in the far, cold future, you can use your stored energy to perform exponentially more calculations, to think more thoughts, and to live more subjective life than you ever could have in the universe's hot, wasteful youth. This paints a truly epic and eerie picture of our galaxy. The most advanced, godlike intelligences are not building Dyson spheres to capture the energy of their hot, inefficient stars. They have already done their work and have gone dark, waiting patiently for the universe to get colder. The silence we perceive is not an absence, it is a deliberate galaxy-wide quiet time. The Fermi Paradox is a failure to understand the ultimate motivations of truly ancient intelligence. We are noisy, impatient, biological children shouting into the cosmos during the middle of the day, wondering why no one is answering, completely unaware that we are living in a library where all the adults are quietly waiting for the cool of the evening. And that is it. If you've enjoyed this video, please consider subscribing to the Purple Files, click the like button, and drop a comment down below. More videos to come, and until then, thanks for watching.